word is, but to get us to this point, having you understand what an average is and what a standard deviation is and what probabilities are really to get you to this point where you can look at it all at once. So when we left off last, I had you guys flipping coins, and I got all the data right here. If you guys want to have it in your TIs as well, I'll put it up here on the overhead. Put it over here. So I had you guys flip, and I believe the question was we flipped until we got heads. Yes.
Yes.
I believe that was so we start with and I'm not sure if I did this right. I think these numbers are right. 243, 60, 31, 15, 6, 30, and 1. I want to say this should have been 0.
I have 1.
Is it 1? Okay, then we'll leave it at 1. That's totally fine. That's totally fine. 1. So 1, 2, 3, 4, 5, 6, and so forth. Say that again?
How do you get the heads without flipping the coin?
Well, because I wasn't sure if we had an initial value of before 0 flips, there were still this many people. See, what I thought was we had flipped 243 times, and 0 would have been, before we started flipping, there were 243 people. After 1 flip, we lost this. After 2 flips, we lost this. It's kind of like we did in 105. I wasn't sure if that's how we did it or not. It's totally fine. So we'll just define X as number of flips, and this guy frequency as those who stopped at that number of flips. It works just fine. That way. I just want to make sure I was consistent. So you're right. You can't flip. You can't not flip and get rid of people. Unless you're the government. All right. Okay, dope. Is that visible enough? I like having the doors open. It does bring a little more light into this weird room, which is okay. So this is experiment number 3, yeah? Because we did 1 coin, 2 coins. Now we're at this. We're going to go to 1 die, 2 dice, coins. We'll go back to dice momentarily, and then we'll switch over to just my mortality, like I said. So experiment number 3. Now this is actually tied to something called the gambler's ruin. Flip a coin until heads. Now what I'll do is I'll come back to this. I'll come back to the gambler's ruin to kind of paint a picture for your quiz next Thursday when we're done analyzing this distribution. So here's the distribution we want. Let's make sure we can see. I think it goes down further. So X is going to be number of flips until heads. And then F is just going to be the frequency count. So we've got 1, 2, 3, 4. I think it goes down to 9 if I remember correctly. It does. It does. 1, 2, 3, down to 9. So these are what we call the random variables. The random variables. Why is it called a random variable? This guy right here is called a random variable. Why is it called that?
Because you know the range of values you're going to get, but you don't know which values.
That's perfectly said, Aaron. You know what you're going to get. And what's interesting about this is, technically speaking, this could go on forever. I mean, technically speaking, there could still be somebody sitting in here from Tuesday flipping the coin that hasn't gotten heads yet. Yeah, God, when's it gonna tails? Ah! Technically speaking, it can go on forever. But realistically speaking, eventually you're going to hit heads. I mean, it might take an infinite amount of time, which is kind of silly to think about. But you're going to hit heads. So yes, I love what you said, Aaron, in that you know the range, you know the values of the variable that it can take on, even if it's infinite, technically. But you don't know which one you're going to get. When you guys are throwing the coin, you don't know if you're going to get heads or tails on each given flip. So you know you're either going to get heads or tails, but you don't know which one's going to come up. That's what makes it slightly bit random. A tie-in would be Gallup going out and doing a poll, trying to figure out who's going to win in 2016. If you care about that, you shouldn't, FYI. You shouldn't care about that right now because they do way too many political polls way too early. But if you cared, Gallup would go out and poll some people. So if they're going to go up to a person and say, who do you support for the Democratic position for candidacy for president, and puts the microphone down, at that point, you know what the choices are. I don't know what they are at this point, but the person would know. And if they don't, they go, I don't know who's running. And then they'll say Hillary and whoever else. I don't know. You know, who knows? And then that person would have to pick one of those people. So you know the choices, Hillary and whoever else, but you don't know what that person's going to say. That's the random part. Does that kind of make sense? So it's somewhat known, but it's also somewhat up in the air. That's the random variable part. All right, frequencies. We got 243, we got 60, 31, 15, 6, 3, and 1, and then we got 2 more. Went 2 and 2. Beautiful, 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 beautiful. So what I want to do first, I want to ignore that column in a minute. That's a great column. I'm glad we did it. That's what the data we collected in class was. But I want to ignore that column because I want to create a probability column, not a frequency column. I want to make it a probability column. So the first thing I want to do is I want to figure out how many total flips we had. So I want to sum all of this up. And there's a quick little trick you can do in the TIs. If you want to see how to do this at break, I'll show you. Sum L2. So you guys flipped a combined total of 363 flips. What I want to do right now is I want to turn these into relative frequencies by dividing them each by 363. So we can do that together really easily. So you're in your stat editor, yes? You're in your stat editor? You're not. Sorry, Rob. You will be soon. You don't worry, you're there, you're getting there. So everybody, if you've got L1 and L2, put your cursor on top of L3. Now what I want you to do is type this. Type L2 by pressing second 2. Then a division symbol, and the number 363. And then press enter. And what you just got now are the percentages that correspond to, okay, 243 of you flipped heads on the first flip. What percent of you flipped? Well, about 67%. 60 of you, what's that? Oh, that's about 16.5%, and so forth. So that would be the percent frequency, or the relative frequency would be those values. Did anybody error out with that? It can happen. You can get errors if you don't do that kind of the right way. Say that again?
Can you do that again?
Oh, sure, for sure. Oh, they put it in L6. That's fine. I'm sorry. Yes, if you had your stuff in L4 and L5, just do L5 divided by 363 and put it in L6. Sorry, I told you to do that, didn't I?
L3.
I told you to put it in L4 and L5, didn't I? I'm a bastard, and then I moved it back. I turned on a couple bastard. Sorry. So you're just telling it whatever column it's in, divide that by 363. So if it's L5, just use L5. I'm sorry. Should I do that? Should I move mine over to L5? Would that make it right? I'm terrible now. Like I just cheated on my friend on the playground. Sorry. So anyway, yeah, whatever it is, just tell it that list divided by 363. So anyway, I put it, should I move it to L4, L5? Would that make it easier? No. Just stop. All right. So back up here, Omar, to answer your question. Clear that out in L4. So we're up in L3. Whenever you do this kind of thing, you have to make sure your blinker's on top of the list name. That's the one thing it's easy to forget, because when you use Excel, you don't do that. You're actually in the cell, and you're messing with the cell. But in the TI, you got to go on top of the list. So I'm going to type L2, second 2.
Can you stop for just 1 sec?
Yeah.
Okay. That division is going quit or go to when I try to put the division symbol.
Did you put divide by 363?
Yes. I put in the L4, but equals, it says equals. Then I put the division sign 363.
What do you divide 363 into?
L4.
You got to tell it that. L4 equals L.
You get to put equals.
So right now, I'm in the same place you are, Kel, right?
Okay.
So I'm on L3.
Okay.
So you said you put divide by 363.
Yes.
Divide what by 363? You got to tell it what to
I
divide.
was dividing L4.
So you have to tell it that. You have to put L4. So you got to tell it second, and I got to tell it L2. So you can't divide 363 into, it has to have an argument to divide it into.
Okay. Second.
So I put L2, divide by 363. Press enter, and then they all fill in. Fair enough? Believable? You guys got very quiet all of a sudden. Week 7. It's week 7, it's allowed. All right, you now have an empirical probability distribution, which is actually kind of slick, right? You have an empirical, I'm going to put the word empirical up there. I keep using this word. I used it on Tuesday, I'll have to. Start with the Princess Bride. I keep using this word. You don't think of means what you think of means. What does empirical mean?
Got it.
Good! Oh, who said that? Give me credit for it. Whoever it is, yes. Data, it was gotten via a study. It was gotten via a study. You did a study, you collected the data, and you reported back. It was empirically collected. I don't know where the root of the word comes from, but it's not theoretical. We'll do the theoretical one in a second. We'll deal with that. that momentarily. So what I want to do right now is I want to copy those percentages in. You don't have to if you don't want to. I want to copy these percentages over to here. Okay, 66 points, about 67%. That's about 17%. That's about 9%. I'm rounding off. 4%. About 2%. Looks like about 1%. I'm losing 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. And then these guys basically round to 0, don't they? The last three. They round off to 0. So you got basically 0.003, 0.006, and 0.006. I'll just throw a little more precision on there. Sorry, JT, I'm using significant figures here.
Now, if I accidentally, not saying that I did, but.
I got this friend. I got this friend. Go ahead.
I erased all those numbers in L2 and replaced them with all percentages.
Oh, that's okay, because we're going to use the percentages.
Okay.
I was only using this data to get this data, Kelly. Honestly.
Okay, good.
Yeah. And what's nice about the TI, I shouldn't say it's nice. It's nice in this respect. Once you do something like we just did, it becomes static data. In other words, if I change the numbers here in L2, it won't change them in L3. Excel would, wouldn't it? If you're in Excel and you put something in column B, and then maybe in column C you say divide all those numbers by 3, and then you go and change the numbers in column B, it'll also change in column C. It's called a relative reference. TI doesn't have those. It doesn't have that capability, which is a good thing sometimes, like when you mess up like I do all the time. It's just not a good thing in general because part of the beauty of Excel is allowing it to make those adjustments. Okay, please, Cody.
Why don't you round, so it took 8 and 9 flips to get the heads.
Yes.
The frequency was 2, so why didn't you round those to 1%?
I mean, don't worry, I'm only rounding for the board. I'm leaving those in the way they are. All the computations we're going to do are going to be in the machine.
Well, I was just curious because for the 6, you rounded that to 1%.
I know I did. Okay. Don't worry. It was just for the board.
Okay.
All the computations are going to be done in the machine, so it's keeping all the precision that we've got in the machine.
Okay.
It's simply just to drop it onto the board. I should have rounded everything to 3 to stay consistent. But don't worry about that. The computation, like I said, is going to be done here and taken care of. What I really want to know, and this is the reason you have a distribution, is, on average, how many times does it take you to get heads? That's the question I want to ask. On average, how many times would it take you, based on our empirical data, our empirical frequencies here, relative frequencies, how many times would it take you until you got heads, empirically speaking? On average, how many times would it take you to get heads? So can we figure that out? Well, sure, we could do it by hand, but I think you had enough of that last time. I'm pretty sure, even though the die thing was cool. Love that. But can we just run it with the machine? This is why I said, Cody, we're going to leave all the computation to the machine. Let's do it with the machine. What are you going to run? You're going to run one bar stats. That's why I said we've been working on statistics. You're going to run one bar stats. Just make sure you pull the right columns, right? So come over here. Yes. Oh, careful. Zoom. I would do L1, L3. Yeah, because we're going to use the relative frequencies, not the frequencies. And the reason for that, you'll see why momentarily. Okay?
So turn my plot on in number 4.
You can't?
No.
Sure you can. Just put L4 in the plot setup. We'll see that in a second. I'm going to come back to that in a second, Kelly, and actually put it up here for you. So L1, L3. Now, if you do L2, there's nothing wrong with using L2. It's just, you'll see why I want to use L3 here in a second. And the reason is, it removes the sample standard deviation when you use a probability distribution. Because the theory is, a probability distribution shouldn't be thought of as a sample, it should be thought of as everything that can possibly happen, which then becomes a population. You might not care about that right now. Or you might not see why that's relevant right now. Please don't worry. That's why I want to get you guys thinking in terms of the frequencies versus the relative frequencies versus the count frequencies. So on average, how long does it take us to get heads? On average, it takes us about 1.67, 1 2/3 flips to get heads, on average. Now, hopefully that makes sense, looking at the numbers. A whole bunch of you were done in 1. And then you started tailing off after that. It tailed off, it tailed off, it tailed off, it tailed off, it tailed off. The standard deviation is one point, whatever it is. I'm not going to worry about the standard deviation very much in this particular case. I'm worried more about the average. I'm worried more about that because I want to talk about what that means. What is the average, again, of any data set, any time? Think of it as, good, what middle? I love that. I love middle. Good. How can I phrase this question? Is it the mostest? Not the mostest. What's the mostest? That's the mode, right? Is it sometimes the mostest? Is sometimes the average and the mode the same? In this case, it's not, right? The mode was actually 1, and the average is slightly to the right of 1. Why is the average slightly to the right of 1? If the mode is 1, why is the average a little bit, almost a 2, right? Why? Why is that? Anybody have good? Say that again, Zach.
Balancing the cookie.
Right, because the balance point, the average is the balance point. So now Kelly asked, okay, I can't get this thing to graph. You can, you have to tell it where to look. So I'm going to set up a quick histogram for you guys of your data, if you don't mind. Quick histogram of your data. Plot 1. Histogram okay? Whoops. Here we go. Histogram. This is where you would tell it to look at L4, L5. Now I'm going to tell it L1, L3 because that's where my stuff is, but you just have to put your different lists here when you set yours up. That's the only difference, my friend. That's the only difference.
And that'll turn the other plots?
It'll turn to the plots.
My plot 4, I have my info on plot 3 and 4.
Yeah, then just put it there, 3 and 4. Yep, all you got to do is tell it where to look. The biggest cause of error in the TI is people telling the TI to look at different places than what the data actually is.
Okay.
Yeah, Eric.
Where do we want it to look?
Well, my data's in L1 and L2,
Right.
wherever your data is.
So I want L4.
I'm guessing, yeah.
Not
I should just
L3.
put this back in L4 and L5. Would cause us to solve this whole problem. Yeah, wherever your data is, tell it to look there.
But I don't want my empirical frequency.
Yeah, I'm using my fractions here. Now, we'll come back to that point in a second. Okay? Now, the problem with this, when you do zoom stat, it does this. This is okay. We finagle, we fix this. But if you guys run zoom stat, who's getting the exact same thing where you get a big block and then nothing? I don't know why the TI does this. I have no good reason for you, but it will. So now we fix. We fix it. We press the window button, and we begin to realize why the TI is doing this. For some reason, even though our data goes from 1 to 9, it goes from 1 to 17 by 8s. That's kind of silly. We want it to go 1, 2, 3, 4, 5, up to 9. So the min of 1, I'm totally down with that. I'm going to set the max at 10. I'm set. No, I'm not. This is just the same thing we've done for the past couple weeks with histograms. We're just breaking up. We're breaking it up.
1 to 10.
And then X scale is going to be 1. Is going to be 1.
That's it?
And then we can try it. If you press graph right now, let's see how that looks. It looks pretty bomb. You might want to finagle more. You might want to cut more of the vertical space off. But that actually looks like your data, doesn't it? You've got this 67% dropping to 17, dropping to 9, dropping to 4, and then it's so small you can't see it anymore. It's down there. It's just the window is so small and the resolution's so poor you can't get down. Michaela, yeah? What error? What error? Stat? Syntax. Go to it and it'll take you right to where your error is and you can fix it. Yep, there you go. Whenever you get a go to it, because it'll take you right to where the problem is. And now you can finagle this if you want. If you want, you don't have to. But you can get into the window, and again, it depends on how much Math 95 and Math 111, Math 105 graphing you did. You can make the Y-min 0. You see how the Y-max is 1.16? The biggest frequency we have is 0.67. So I'm going to change it to 0.7. Because it'll fill the window better like that. You press graph, there. Now you actually see some of these guys over here. All we're doing is changing the scales, that's all we're doing. Yours might look different, that's fine. That's fine, the key is that we see the distribution. And you can see, friends, why the average can't be here at 1. Because if your average is here at 1, the cookies crash the tray down that side. You have to move the balance point over closer to 2. Because that's going to keep this crazy. There's data in all of these spots. Not much, but there's enough to pull the average over there. So that's why your average is a little bit right of where your median and where your mode are. Ask me questions. Ask me questions. Eric, what's up?
I'm lost. I don't know what we just did. I was trying to figure out.
Well, here's the thing, and this is a good math skill thing to learn. We did nothing new. Think about this. It might seem new, but we did nothing new. We ran one bar stats on weighted data, correct? L1, L3, that's versus L1, L2. That's nothing new though. And then we did a histogram. So try to think of this, and I understand it's a new word, probability distributions. I understand that. But connect it to the old stuff. All you're doing is you're finding a weighted average, right? Think about that. You're finding a weighted, we did it by hand Tuesday. I think we understand how it connects that way. All we're doing is we're using technology to do it for us. If you're getting errors, we can fix them at the break, happily. But this is just a histogram of what we're looking at over here. That's it. So, is it that you're getting errors, Eric? We can fix them at the break for sure if you're getting errors.
No.
Okay, then we can, whatever the question is, we can get it at the break. Ask me questions about specific parts of this. Do you see why your average is shifted right? Because the data is highly skewed. Highly skewed. Highly skewed. That doesn't matter though. That doesn't matter. It still has an average, whether it's skewed or not. Now, what does this have to do with what's called the gambler's ruin? Well, this curve, or something like it, and the something like it we'll get to in a second, there's a guaranteed way, I think you guys won't know if I've heard this before, there's a guaranteed way to win $1 if you have a friend who's willing to bet with you and a coin. Take a coin up to your friend and go, here's $1. If I flip heads, you have to give me $2. Okay? But if I flip tails, you can keep my $1. With me so far? So you flip a coin, and if you flip heads, he gives you $2. But if you flip tails, he gets to keep your $1. So let's say you flip tails, and your friend has your $1. Like, crap! He's got my $1. Let's do it again, best of 3. And you double down a bet. This time you bet $2 to your friend. $2. And you say, okay, flip it again. If I get heads, now you pay me $4. Now you've already spent 3, right? You spent $1 and then 2, which means you spent 3. But if you get heads this time, you're going to get 4 back from your friend. 4 is going to offset 3 plus 1, which means you won $1. If you flip heads. What if you flip tails? Now you're in the whole $3, right? So what are you going to do? Okay, do it again! Bet 4. Bet 4, right? So now you're in the whole 7. 1 plus 2 plus 4, you're in the whole 7. But if you flip heads, he now has to give you 8. But if you flip tails, and you see how 8 wins you $1, you're in the whole 7, you win 8, you profit 1. Okay, then you can stop bet, I guess, at that point. But if you flip tails, now you're in the whole $7. So you bet 8. Now you're in the whole 15. Now, this seems ridiculous, and you're laughing at it, as you well should. This is exactly what people in Vegas do without realizing it. If I just play again, if I just play again, if I just play again. The problem is, you will always win $1 if you play long enough. But think about how much money you spent to win the $1. You see? You're always going to win $1 if you play long enough. It might take 32 flips until you get that heads, but you'll always win that $1. But if you played 32 games, you spent about $1.5 million to win back that $1. Is that sensible? This is the distribution that governs that. This is the distribution that governs that. Theoretically speaking, we could have gotten this distribution without even flipping the coins. So if you guys are getting hung up on the data, there's an easy fix for that. Watch this. Let's do the theoretical. Let's do the theoretical real quick. Over here. We'll do it in a different color. Theoretical percentages. Theoretical. So, we know in our data, 67% of us were done after the first flip. Now, suppose we didn't run the experiment last week, or last class on Tuesday. Suppose we just said, imagine everybody in the room flips a coin. And there's 40 people in the room. So there's 40 people in the room. That makes a nice even number. How many heads are you going to get? How many heads are you going to get? What would you expect to get?
On average over time, 20.
On average over time, 20. Why 20?
It's 50%.
Half. Shouldn't this be a half? 50%? 0.5? I mean, doesn't that make sense? On average over time, you'd expect half the coins to come up heads and half the coins to come up tails each time. So in other words, the number of flips until heads, 50% of the time it should take one flip. Because after one flip, half the room has flipped heads and half the room has flipped tails. Is that fair enough? We're starting with a value of 1 being one room. Fair enough? Okay. Suppose we go to 2 flips. What percentage of the room should have to go to 2 flips? What do you think? Now remember, think about it not mathematically, but contextually. We just flipped 40 people. 20 of them flipped heads and they're done.
1/4.
20 of them have to flip again because they flipped tails. What's going to happen to that 20? Half are going to get heads, but half of 20 is now 10 over the original 40 is 1/4. So shouldn't this be 1/4? 1/4 theoretically should take. So of the room of 40, a half of them are going to be done in one flip. A quarter of those that of the room, of the ones that haven't been flipped out after one, are going to take 2 flips. So now you've gotten rid of 30 people in the room. There's 10 left, yeah? There's 10 left. Have them flip again. What's going to happen to those 10 on average over time? Half of them are going to flip heads, and half are going to flip tails. So half of a half is now a quarter of a half, which is an eighth. That sounds like a lot of ridiculous math. And also rhyme, like Dr. Seuss. So it went from 40 to 20, 20 to 10, 10 to 5, 5 over 40, that's an eighth, right? 1.25 or 0.125? Are you seeing a pattern? Are you seeing a pattern in this? What's the next frequency going to be? The next? The next? And this is what's so cool about this. As you keep going, this will never get to, it can't, can it? It will never get to 0 because there's always a chance that someone keeps flipping tails. There's always a chance that someone can keep flipping. There's no guarantee they have to flip heads by a certain amount. It's unlikely that they're going to flip heads 32 spots down the road. But it's unlikely that that's going to happen. It's unlikely that that's going to happen. Now suppose I asked you to average the theoretical distribution. Suppose I asked you to average that theoretical distribution. This does get challenging. Because theoretically speaking, you'd have to be entering numbers forever into your TI, right? This wouldn't stop at 9. This would go 10, 11, 12, 13, 14, 15, all the way down. And fortunately, if it ever gets to that point with you guys in your careers where you have to deal with a distribution like this, which you will deal with, I have a quiz for next week called The Gambler's Ruin that deals with it. And I show you how to deal with it in part. There are equations you can make up that model the behavior pretty well. We did it in 105 a little bit with exponential modeling back in 105. We tested it a little bit. So the equation for this, these would be probabilities, right? P of x. P of x's, if you want to call them using the formal language, P of x. The equation for this, it's kind of nice actually. It would just be 1/2 to the x power. See if you can make sense. See if that makes sense to you. This might call on your Math 111, it might call on your Math 105, it might call on your Math 95, I'm not sure which class it would call on. But do you see how if we plug these values of x into that equation, you get these values of y? If you plug in x equals 4 to that equation, you get 1/16. 1/2 to the 4th power. 1/2 times 1/2 times 1/2 times 1/2 is 1/16. If you plug x equals 9 into 1/2 to the x, you get 1/2 to the 9th, which is, I don't know, 1/256 or something like that, and so forth and so on. So the problem is, why it's called the gambler's ruin, is because since that goes on infinitely, there's always that chance you have to measure that that will happen to you. The average, FYI, if you actually did average this distribution out to infinity, it comes to 1.5. The average is exactly 1.5. You guys were damn close at 1.67. Damn close. The exact average is going to be 1.5 exactly. And yeah, I'll show you how to get at that at the quiz next week. It's like this extended. But the idea is, it's the same as when you do it empirically. It's just weighted data, weighted here. Same as a GPA, same as every other weighted average you've ever taken. That's it. That's the only difference, is that it's percentages versus frequencies. Everything else is identical. Yeah? Gambler's ruin. And you all laughed at it. As soon as I started describing the experiment, you're like, that's idiotic. Why would you do that? I don't know. Ask 95% of people in a casino why they're sitting there. I just play again. Have you ever watched Deal or No Deal? It was in a show. I had to stop watching it years ago. It came on Howie Mandel. Loved the guy. Loved him for years when he had hair, when he doesn't have hair, whatever. Watching those people play that game drives me insane. Because one of the most common things I hear on it is, keep playing. Don't take the deal. You've come this far. Keep going. No, you have to know when to stop. That's kind of the key. There is a point beyond which you should not go because on average you've maximized your winnings. But the Gambler's Ruin shows you that. It shows you that. On average, 1.5. 1.5 is here. Once you get past that, it's diminishing returns, yes? It's diminishing returns past that. That's the whole point. Yes, I may have to play 8 times to win my dollar back, but in that 8 times I've spent $100 to win a dollar back. Yes, I'm up $1, but I spent $100 to do it. It seems kind of stupid, doesn't it? It seems kind of like a waste of time and energy. But that's precisely what people are doing in casinos, or hoping to do in casinos. That's assuming they actually do have the big hit that pays off all their debt, which, as we know, doesn't always happen. We know that doesn't always happen, right? It's unfortunate. Ask me questions about this. I do want to change it, because you guys just got kind of like quiet all of a sudden. Kelly, ask me that question. I saw your hand. I saw your hand move. No.
No.
Oh, you must have moved your glasses.
Yeah, probably.
Okay, sorry, I'm like an infinity motion. Good? All right, let's change scenarios. Any other questions before I change? I do want to change the game. I want to change the game, and then I want to change the game completely to actuarial work, which is the most interesting part. This is all just theory at this point. All right, back to dice.